Okay, so thank you so much, Jan. So I'm going to now dive deeper into an example of how to link climate data to a household survey with some technical instruction using R. And this is a very challenging task. Okay, so here are a few learning objectives for this portion of the workshop. So first, I'll just define some existing data gaps, specifically as it relates to studying how climate changes impact food and nutrition security. And then I'll go over some key differences between spatial and survey data and identify the necessary steps that are required to do these data linkages. And then finally, we'll see how to apply these steps using R. So we have an abundance of continuous data available now in the public domain that pertains to the climate that spans decades. And most of this data is geospatial, coming from satellite imagery. Other sources are weather stations or weather balloons. And when it comes to disasters, we often see databases that are created based on media reports, which provide an important source of information. However, this type of data lacks the same type of spatial granularity that we see that comes from satellite imagery and other sources. Some surveys have actually started to incorporate people's experiences with natural disasters, but this is not very common, and typically it's not available longitudinally. And when it comes to population data, there are many health and economic and nutrition surveys available. In contrast to geospatial data, population data is usually self-reported and usually requires direct interaction from a person or a field team. And these data are often collected via web or mobile, web or paper-based surveys or phone interviews. Data may also come from government sources such as the census or data from other agencies or from existing records, for example, hospital data warehouses. And while it can be longitudinal, it generally doesn't have the same continuity that we see with geospatial data. So what we have are two very different types of data gathered from different perspectives, but what's missing is this gray area in between and a lack of, there's really a lack of multidisciplinary data sets that allow us to evaluate questions about how climate and disasters impact specific human outcomes. So our task is to create these data sets. And there are many different data formats available, and I'll define these shortly. Ultimately, for those of us with the public health or nutrition type backgrounds, we want a data set in a common format that we can use for statistical analysis. The challenge is that these data are usually very difficult to connect, and Jan talked about this in his talk, because they often lack a common attribute. So it's not impossible, it's just very difficult. And today that's what I'm going to focus on using this raster data format, which I'll define. So two primary types of geospatial data are raster and vector. So raster data are a series of grid cells where each cell has a value representing the feature being observed. And it's usually depicted as an image and available as a GeoTIFF file. And raster data is best suited for continuous data or information that does not have hard boundaries or locations. This is the common format of climate data from remote sensing imagery, measuring things like temperature, precipitation, or other variables. In contrast, vector data is represented as either points, lines, or polygons, for example, country boundaries or roads. And shapefile is a common format for storing this type of vector data. And statistical software programs, in case you're not familiar, these are tools that are designed for different data management and statistical data analysis. Each have their own user interface and programming language. And when it comes to population surveys in the public domain, we usually see either Stata or SAS formats. So today I'm going to focus mostly on R and how to do this data linkage using R. So I want to highlight for those who are not familiar what this interface looks like. So on the top left, so this is just an example of the R interface. And on the top left is where you write your script. On the bottom serves as the log in the results window. On the top right is where you can see a listing of the data sets and objects. And when you create plots, they appear on the top bottom. And one of the things I want to highlight with R is that it's the only free open source statistical software. One of the main strengths is its versatility through an abundance of packages that the user can install, and including for spatial analysis. So I've already defined raster data, but here's an example. And one key feature that I want to highlight is that it can be highly granular. So you can see the gridded format where each cell represents a value, and depending on the sensor or the pixel size, it can be quite high resolution. And so this is the example raster data set that I'm going to use today. It's very high resolution data taken from the Global Surface Water Explorer, and shown here is Central Java, Indonesia, with a zoomed in view to the right. So the gray outlines that you see are the districts that I've overlaid with the polygon data, and the green and red are the colors representing the variable, the raster variable being shown. So it describes where surface water has occurred, increased or decreased, or remained the same between 1984 and 2021. So very high resolution data that we're going to link to a survey. And here's another example of raster data, just showing an analysis done using NV software, which is a common tool for remote sensing. Okay, so you can see here what a typical survey data set structure looks like. And so what I want to point out here is that the level of the unit of measure is household. And the level of spatial aggregation is based on administrative boundaries. And it's intentionally coarse for ethical reasons. So, right, it's not ethical to put the exact locations of someone's household along with lots of information about that household out there for everyone to see. So this is the challenge with linking data. So in this example, this is just from the Indonesian Family Life Survey. It's showing the smallest level of aggregation is the district where the households live. So that's what we're going to need to use for linking. So, and now we come back to this question of how to link these two very different types of data. And the main thing that we need is a variable in common, so a temporal or spatial attribute or both. And usually it doesn't match perfectly, so we need to be creative. And now I'll just go over the steps that are involved in this process for linking a raster data to a survey. So first, you need to download the data, and you need, this is important because you need both the raster data file and a vector data file or shape file representing the geographic boundaries. Next is masking and cropping the raster by the general area of interest. So in the example I'm showing today is Central Java. So it could be country or province level. Then you extract and summarize the raster values by the geographic boundary you're going to use to merge. In other words, you're creating that common attribute so that you can link it to the survey. And in the example I'll show, the survey has households with districts where they live, so I want to summarize the raster values by each of the districts. And then you export or save it as a data set where the rows represent the geographic boundary and the columns represent the summary statistics that you've created. And finally, the data can be merged by that common spatial attribute. So in this example, I'll show how the high resolution Global Surface Water Explorer data, which describes the spatio-temporal distribution of surface water since 1984, can be linked to the Indonesian Family Life Survey, which is a longitudinal health and economic survey of the Indonesian population dating back to 1993. In this example, the Global Surface Water Explorer dataset does not vary over time. So rather, it captures the overall changes throughout that time period. So the linkage is just going to be made based on district and not by time point. But in practice, you may need to do both. The same principles apply. So first, downloading the data, I just wanted to show here how you download the spatial data. So as I mentioned, you need both the raster data and shapefile containing the administrative boundaries. So to the left is the example of the data download process for Global Surface Water Explorer. And the raster data are downloaded as tiles shown in the grid, and the data are downloaded as TIFF images. And then on the right is an example of where you can obtain shapefiles for administrative boundaries, and there are many sources for that. Okay, so now getting into a little bit more of the technical piece. So after downloading the spatial data, it can be loaded into R using the SF and raster package, which you see on lines 8 and 9. You can see here I had to read both the raster and the shapefile, and then you can plot the data to view it, which is shown on the right. And here the raster data values range from 0 to 100, and these are discrete values where 0 indicates not water and then 100 indicates 100% recurrence over the period. So you can see I've subset the vector data of the boundaries to Central Java, which is my area of interest, on lines 21 and 22. And I've done this using two levels. One is just the province boundary for cropping the raster, and the other level is the district boundary, which I'll use to summarize the raster cells. So next, the raster data is cropped to Central Java and masked to produce a raster map of just Central Java, which you see done on lines 26 and 27. So you can see the masked output in the plot at the bottom. And this cuts down substantially on the processing time for the next step. So this is one of the more challenging tasks, which can take a very long time if you use traditional tools like GIS software with the toolbox. And I'm talking about the point and click tools on GIS, which I think you would use converting raster to point. And I actually did try that before I moved to doing this in R, and it ran all day. I let it run for probably 12 hours, and it was still just tiny bit done. So it takes a lot of processing time with such high resolution data, but with R programming, this task can be simplified by using the exact extract R package on the masked data from the previous step. And I think there's other ways to do this in Python. I'm not as familiar with Python, but I know I have some colleagues, fellow PhD students that probably can tackle this in Python. But with R, the exact extract R package works really well. So with this package, you can obtain many different summary statistics, including a count of the raster cells within each district, a sum of all the values, and the average, and many others. You can also obtain a listing of the individual data values so that you can do your own types of summaries, which is not shown here. And then lastly, well, not lastly, before you get to the merging, you want to save your newly created data as a data set that you can use to merge, or you can do the merging in R. In this example, I'm saving my data set in Stata format because that's the format that my survey data is in. But you can save it to any format. But what you can see here is after the extraction and summary process, that you've created a data set where each row now represents a district, and each column is a variable containing the summary information of the raster values within that district. And now you can do a simple merge. And so this is an example in Stata. Now you can just do a simple merge based on the district. And it contains both the household level information from the survey and information about the changing environment in which the districts live. And so what you've ended up with is a multidisciplinary data set where you can now address a range of questions that previously were not possible. So here's a listing of some sources of climate and disaster data that I want to highlight. And there's many available. But as I mentioned previously, I mean, there's a whole range of data now in the public domain. And as scientists, it's our task to use these data to study different things. And so I want to actually highlight the last bullet, which is NASA's Socioeconomic Data and Applications Center, which I've not yet worked with that data yet, but I saw recently that they've created the first ever global poverty grid. So a raster data set that has information about poverty. So it opens up many opportunities for data linkages and multidisciplinary research. And I think we're out of time and I'll stop there. So thank you.